Good evening. Today we are going to discuss a topic called normal subgroup. In the last class, நம்ம வந்து group, subgroup, semi-group, cyclic group, permutation group இந்த மாதிரி நிறைய groups அதனோட ப்ராப்பர்ட்டிஸ் ப்ராப்ளம்ஸ் அதெல்லாம் பேசணும். இன்னைக்கு நம்ம பேசக்கூடியது வந்து நார்மல் சப்குரூப். இந்த டெஃபினேஷன் ஜிங்கிறது ஒரு நான் எம்டி செட்டு, என்னங்கிறது இங்க வந்து பாத்தீங்க அப்படின்னா என்னங்கிறது சப்குரூப் எடுத்தீங்க அப்படின்னா அது எப்போ வந்து நார்மல் சப்குரூப் அப்படின்னு சொல்றோம். லைக் ஸோ இங்க பாத்தீங்க அப்படின்னா லைக் ஹியர் இந்த சிம்பிள்ல இந்த மாதிரி சிம்பிள் இருந்தா அது சப்குரூப். ரைட், n is a subgroup. When we say that a subgroup is a normal if it satisfies this condition, gn equal to ng for all g belongs to g, or gn g inverse belongs to n for all g belongs to g and n belongs to n. The trivial examples are a singleton element E and the whole group G. சரியா? In that case, we used to denote it as n is a normal subgroup of G. N is a normal subgroup of G. Next, we will define what is meant by simple group. A group is called simple if its order is greater than 1, in which only one normal subgroup. Okay, that is identity and the group. Right. Next, we define what is meant by conjugate element. What is meant by conjugate element? Consider a non-empty group. Take an element x belongs to G. For all x belongs to G, Gx G inverse is called conjugate of x. Gx G inverse is called conjugate of x. Conjugate of x by G. Right? So we define what is meant by normal subgroup, simple group, and conjugate. Some of the results based on normal subgroup. Suppose consider a group G, n is a normal subgroup G. In this case, the left cosets are equal to the right cosets of n in G. Left cosets of n in G are equal to right cosets of n in G. Okay, right. This is the first result. Second result is if G is a finite group and n is a normal subgroup of G, then order of G by n equal to order of G by order of n. Order of G by order of n. This is a very important result we'll be using frequently. Right? Next, every subgroup of an abelian group is normal. We know what is meant by abelian group. Consider a group G if it satisfies abelian condition, which means commutative property. Then we call it as abelian group. Consider every subgroup of abelian group is normal. Right? Okay. The next result is center of a group. Z of G is a normal subgroup. Z of G is a normal subgroup. Okay. Next result is consider group G and H and G are two normal subgroups of G, then intersection of two normal subgroup is again a normal subgroup. Here we have to listen. Intersection of two normal subgroup is also a normal subgroup. Okay. The next one, based on the index we are going to define. Already we recalled what is mean by index. If not, you go and recall it. Every subgroup of index 2 is normal. Particularly, index 2 is normal. Every subgroup of index 2 is normal. This is also a very important result. Okay. Right. Next one, if consider a group G and N is a N is a normal subgroup of G such that the number of elements in N is small n. Then intersection of all the normal subgroup forms a subgroup H. Again, that subgroup is also a normal subgroup. That means if we take a group and consider collection of all subgroup, which is a collection of all normal subgroup. If you take intersection also, the intersection resultant is again a normal subgroup. Okay, so we have discussed several results based on our textbooks. Now we are going to use these results to solve a particular problem which has been already asked in TAFR or JAM examination or NET examination, so on. Example, prove that set of all integers, rational numbers and real numbers are subgroups of C. Subgroups of C. That is normal subgroup of G. We know how to prove normal subgroup. Right? Here we have 7 results which we are going to use to prove these kind of problems. Whether Z is a normal subgroup or Q is a normal subgroup or R is a normal subgroup. That's what our question. Here, set of all integers under any operation under addition or under product is an abelian group, which we already know it. Okay. Just now we have seen a result. Every subgroup of an abelian group is normal. Every subgroup of an abelian group is normal. So the subgroups are maybe 2Z, 3Z, 4Z, so on. So that is generalized as MZ. Okay, where M belongs to set of all positive integers. Since by the statement, one can able to say that all the subgroups here MZ are normal subgroup of Z. Okay, right? So Z is a normal. So all the subgroups of Z are normal subgroup. The union are also normal subgroup. So here Z is a subset of rational numbers. Again, rational numbers can have every subgroup which are all normals. Because again, Q is also a abelian group. Again, we repeat the same process what we have discussed before. Right? What we have discussed earlier, the same result have been doing the same. Right? So similarly, we can prove set of all real numbers is also a normal subgroup of a group of complex numbers. Right? Next problem is set of all even permutations. An is a normal subgroup of n. We know that order of an equal to n factorial by 2 and order of Sn equal to n factorial. So by this background, we are going to solve this problem. Right? So see, So Sn upon An by using the order of G by H equal to order of G by order of N. Sorry, here it is a N. Order of G by N equal to order of G by order of N, where N is a normal subgroup of G. This is the result which we have discussed already. Right? Suppose this condition is satisfied, then N is a normal subgroup. This is a if and only if condition. So we are checking whether it is N is a normal subgroup or not by using the previous results. If every subgroup have an index 2, then it is a normal subgroup. Right? See, order of G by N equal to order of G by order of N. The same formula has been applied here, and modulus of Sn equal to n factorial, and modulus of An equal to n by 2 factorial, we will be getting 2. That means the index, this is a definition called index. So index of this is 2, therefore An has an index 2. We know that every group of index 2 is normal. We already familiar with the result. Therefore, An has an index 2, which is hence by using the statement An is a normal subgroup of Sn. Okay, clear? Right. Now we'll go back to the next problem. Consider a group G, which is Z20. Verify how many normal subgroups are there in Z20. How many normal subgroups are there in Z20? So, what is your expectation, or what could be the result? Let's see. Here we are going to use the concept called cyclic group. Again, we know that what is meant by cyclic group. If a group G has been generated by a single element A, then the group is called cyclic group. The A is called generator of a group G. Here G equal to Z20. So Z20 is a cyclic group, right? And every cyclic group is a abelian group. By using the notion, Z20 is a abelian group. And again, we have the another argument that every subgroup of a abelian group is a normal. Therefore, all the subgroups of Z20 are normal. So we can able to find out the number of subgroups of abelian group is tau 20. So tau 20 can be calculated by 12 like this. Tau of 2 square into 5. We can directly like this. 2 plus 1 into 1 plus 1, which is 6. So number of subgroups of Z20 is 6. Hence, we can able to state that Z20 has 6 normal subgroup. Okay, listen one more time. Z20, we have taken a group Z20. We are checking how many normal subgroups are there in G. So we are using every cyclic group is an abelian group. All subgroups of an abelian group is normal, and tau 20. These three concepts have been used to prove this problem. Another one example from a dihedral group. In the last class, we discussed extensively about a dihedral group. What about Dn, order of Dn, the elements of Dn, and what is called reflection, and what is called rotation, and what are the identity elements. All those things we have discussed. Now we are taking a group D4. Since here Dn equal to 4, so we know that number of elements is the order of Dn equal to 2n. Hence, here order of D4, which is 8. So in Dn, we have totally 8 elements. and the radiant is 2 pi by n. So the theta formula. So here n equal to 4. So the each rotation will take a angle of 90 degree. Therefore, we start with R0, R90, R180, R 270. Again, if you add 90, again you will end up with R360. It is nothing but R0. And horizontal, vertical, and this diagonal and opposite diagonal. This is D and D dash. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements. Okay, it is very simple and we can easily remember. Okay. So now we'll see what are the subgroups of D4. Here, the first subgroups are trivial, that is identity. The second subgroup is again the whole group. So this is one layer, H1, H2. What about H3? H3 is R0, R90, which means rotation with respect to 90 degree. Right? Again, R360, which is equal to R0. Okay. So this forms a third subgroup, which is H3. Let us see whether it is a normal subgroup or not. Okay. By using the same formula, order of G by N equal to order of G by order of N. So there's nothing but the index, finding the index. So G is H3 equal to order of G by order of H3. It is nothing but order of G is 8, order of H3 equal to 4, you will be getting 2. You will be getting 2. Therefore, every group of index 2 is normal subgroup. So by using the concept, we can be able to easily prove that H3 is a normal subgroup of D4. Right? Again, H4. H4 is nothing but R0 and R180. R0 and R180. So it is equal to Z of D4. It is also a normal subgroup. H5, H6, H7, H8. Again, we are going to define more 4 groups. Rotation angle with the horizontal axis, rotation angle with vertical, rotation angle with the main diagonal, rotation angle with opposite diagonal. It's a principal, it is a non-principal diagonal. So these 4 sets does not give a normal subgroup. It is not going to give a normal subgroup. You can easily verify. Then H9 and H10. H9 is with respect to 2 shift R0, R180, horizontal, vertical, R0, R180, principal diagonal, non-principal diagonal. These are all normal subgroups. Therefore, identity and the whole group and the fourth element, right? And H4 and H9, H10. So these are all 6 normal subgroups. Therefore, D4 has 6 normal subgroups. So we discussed extensively about normal subgroup and its related concept for your practice. Again, you can take classwork, which is find all normal subgroups. Find all normal subgroups of D3. You can able to find it easily, and you try to hold this. It doesn't matter, right? So you take one by one, D2, D3, even D5, D6. You can take one by one. You can easily prove this. Okay. I'll go at the last one more problem for this, which is asked in the examination. If G is a group of order 2022, H and K are subgroup of G, okay, with the order 337 and group K is 674. If H union K is also a subgroup, H union K is also a subgroup of G, then which of the following is false? Then this is a question. Option A, H is a normal subgroup of H union K. B, the order of H union K is 1011. C, the order of H union K is 674. And the last one, K is a normal subgroup of H union K. Listen properly. So here the given concept is if G is a group of order 2022, H and K are subgroups. H and K order is given, and the union of two subgroup is again a subgroup. Then which of the following statement is false? One is H is a normal subgroup of H union K. The order of H union K is 1011. The order of H union K is 674. K is a normal subgroup. We'll see one by one. Solution. Again, G is a group. H and K are subgroup of G. And so here H union K is a subgroup. From this, we can able to say that either H is contained in K or K is contained in H. If H union K is a subgroup, then any one of the result is true. Now, given G is 2022, which can be rewritten as 2 times 3, 2 cross 3 cross 337. 337, because already order of H equal to 337, which is given. Order of K equal to 674, which is given already. So by this, I'm taking a hint that so therefore, so H union K is a subgroup of G if and only if either H is contained in K or K is contained in H. Okay, but H is contained in like K or K is contained in H. Here, order of K is 674, which is greater than order of H. Therefore, from this, we can able to say that H is the smallest group which is contained in K. H is the smallest group which is contained in K. Okay. Therefore, you go for the option we'll go for the option here. Here, H union K, since H is contained in K, but modulus of K is 674. Right? Therefore, model of H union K is nothing but modulus of K, but is nothing but 674. So in that case, the order of H union K is 674. The option C is true. So if this is true, obviously this is false. Right? This is false statement. So now we are having A and D to be checked. Okay. We know that every subgroup of index 2 is normal. Right? So we recall every subgroup of with index 2 is normal. Therefore, H union K, H is nothing but order of H union K by order of H. That is, order of H union K is 674, order of H is 374, which is 2. Therefore, this value is 2. Hence, what we can say, H union K is normal subgroup of H. Okay. Oh, sorry. H is a normal subgroup of H union K. Right? And we already know that every subgroup, every group is normal to itself. Therefore, K equal to H union K is a normal subgroup of H union K. So K is a normal subgroup of H union K. Therefore, option A and D are H is a normal. So here K is a normal subgroup of H union K. Let's see what are the results. A and D. So K is a normal subgroup of H union K. Therefore, this is true. Right? And H is a normal subgroup of H union K. Therefore, right? So this is also true. Therefore, the false statement is B alone. Okay, this is only B. So like this, we can able to solve several problems based on normal subgroups. So in the next class, we will be discussing some more problems on homomorphism, isomorphism. Right? Thank you. You go for any CSIR, NET or JAM, any one of the examination, pick a problem, use the same concept, try to solve it. Thank you. We'll meet in the next class.